Hello, welcome to Fluent project number one for our group, which consists of myself, Francisco Gonzalez, and Robert Perez. Starting off with part one, we have 2D flow simulation of combined Poiseuille and Coet flow. Starting off, we want to drag our fluid flow element over here onto our workbench, and we want to start modeling our design. In order to make this a little simpler, we just want to change our units over here to millimeter. Come over here to our XY plane. And begin sketching our rectangle. From here, we want to dimension the rectangle to meet the needs specified. We're going to go ahead and make the height 5 millimeters. Go ahead and make the length 150 times 5, which would be 750 millimeters. And that should give us, go ahead and give us our material. So go back to modeling, just make sure to go ahead and make that surface from sketch. And generate. So there you go. We have our shaded in region. That's what we're going to be modeling the flow over. All right, so we're going ahead and going to be done with this. So I just want to make sure to save this. Save project. Project one. And we want to come over here and start running our mesh. Might take a minute. All right. Now that we have our mesh over here, we want to go ahead and define our edges. Obviously, we have our inlet over here. Top, bottom, and of course, we also have the outlet. Just verify that all those are created. All right. So we want to go ahead and insert a refinement to our mesh. We want to go ahead and select all 4 edges. As such, add that to the selection, and then increase refinement to the maximum, which is 3. I'm going to go ahead and generate that. We want to go ahead and change our element size to 0.001. It's fine. And go ahead and, oh, sorry. There you go. And then go ahead and close our mesh. take a minute, and then go ahead and just update that. Might take a minute. Beautiful. Now that our mesh is done, we can go ahead and open up our setup. Want to add double position just to make the results more precise. And then since we have 20 cores, we want to go ahead and make our solver processes 19. I'm going to go ahead and start that. Just gonna give it a second to load. Beautiful. Perfect. All right. All right. Now that we're in our setup, we want to go ahead and change our viscosity. Make sure this is laminar since we're dealing with laminar flow. And ensure that multi-phase and energy are off since we are not dealing with that at the moment. And we also want to go ahead and change our boundary conditions. At the inlet, we are going to be having a free stream velocity of 5 meters per second. So you just want to go ahead and apply that. Apply and close. At the outlet, just want to make sure that our gauge pressure is 0, and it is. So you want to go ahead and close that. At our bottom, you want to ensure that it is stationary, which it is. So we can go ahead and close that. And then at our top wall, since that wall will be moving, make it a moving wall. And make sure that speed is 3 meters per second as specified in the directions. Go ahead and apply that and close. Now let's go ahead and head on over to initialization. I want to ensure standard initialization. I want to go ahead and use hybrid initialization and change our number of iterations to 100. Okay. And then we want to go ahead and run this calculation and make sure our number of iterations, we want to do something big, so let's do 2500. You should be able to handle that. Go ahead and hit calculate. wait for that to finish calculating. Now that those calculations have run, we just want to go ahead and exit our setup. Now that we have run our results, we want to go ahead and insert our velocity contour. As you can see, we have our velocity contour here. You can see that near our bottom boundary, since it is not stationary, the no slip condition makes it so that velocity is 0 meters per second. Over towards the top, since that boundary is moving, you're going to be able to see that our top is close to about 3 meters per second. To go ahead and insert our velocity vector, we want to go ahead and add that. Oh, that already exists. So let's do velocity capital velocity. Okay, that already exists. So let's go ahead and do velocity test. At our vector of velocity test, we want to make sure that location is symmetry 1. We want to make sure our variable is velocity, which it already is. And we're going to go ahead and uncheck our velocity contour to be able to see that once we're done with it. We want to make sure our reduction factor is 1. And our symbol, when I come over here to the symbol, our symbol size is, we're going to change that to 0.1. And we want to go ahead and apply that. As you can see, well, there are a lot of vectors and they are very bunched together, but you can see it. So in that case, maybe I should change the symbol size to 0.01 and apply. Go ahead and apply that. Yeah, that'll make it a lot more visible, as you can see. All right, and then in order to go ahead and include our pressure contour, we want to go ahead and add another contour, label that pressure. I'm going to go ahead and uncheck our velocity test contour so we'll be able to see the pressure contour when that's done. We want to add our location to once again be symmetry 1. Our variable is going to be pressure, so that's already good. That's global, that's perfect. And then we want to go ahead and do 200 contours. And go ahead and apply that. And if we go ahead and zoom out, should be able to see that very well. As you can see, it starts off with a high pressure, and then as the boundary layer forms, as the boundary layer develops, the pressure drops. And as a matter of fact, if we add even more contours, that should be able to smooth out even more. Hopefully we can sustain that. Yeah. In order to chart our velocity profiles at the mid and end point, we want to first and foremost add 2 lines. Our first line is going to be our midline. And that is going to be obviously at the middle of our section. Obviously, we're doing 750 millimeters, which in meters, that would be 0.750, and then divide that by 2. That would go ahead and be 0.375. 375. And then 0.2 will be the same, 0.375. However, that's going to have a height that spans the entire boundary. So we initially set our height to be 5 millimeters, which if we go ahead and take that in meters, that's 0.05 divided by 2. That is 0.025. 0.025. And then let us uncheck our pressure in order to be able to see that line. Oh, never mind. No, not taking that divided by 2. We're doing it across the whole span, so it's just going to be 0.005 as such. Apply. There you go. Now that spans the whole line. And now that that's applied, we can go ahead and add the line for our endpoint, end line. Click OK. That's again going to be 2 points. Our length is 0.750 meters, 0.750 meters. So I'm going to do 0.749. 0.749. 0.749. Oh, 0.749. And then that's going to be at a height of, once again, 0.005 meters. You should be able to see that all the way at the end. There you go. Beautiful. Now that we have those lines set up, I want to go ahead and insert our chart. We want to go ahead and name that just for reference sake, velocity profiles at mid and end. Click OK. So our data series is going to consist of our midline. Let's go ahead and capitalize that, midline. Choose our midline. Again, go ahead and add our end line. And then choose location of end line. Beautiful. Once that's applied, we can go ahead and choose our x-axis variable to be velocity in the x direction, and then our y-axis variable to be our y value. If that's applied, you can see velocity at the middle midline, which is the red line, and velocity at the end line, which is the blue curve over here. And these results make sense because Obviously, um, it has not formed. It is still, if not in development, or at least more so, the end line would be more in development or fully developed as compared to the midline. Hence, the slightly slower velocity. That will be part one for our project 2D flow simulation of combined Poiseuille and Couette flow.